This video is going to cover Chapter 2, Chemistry. Chapter 2 is actually a very heavy chapter as it goes through two major sections. It goes through basic chemistry and it goes through biochemistry. So it's going to go through both of these parts. With that, it's a very heavy chapter. So basic chemistry is going to be part 1. And this part 1 is going to be from 2.1 all the way to 2.5. And then the biochemistry section will be from 2.6 to the end of the chapter at 2.12. So because this is a very heavy chapter, what I'm going to do is I'm actually going to split these videos into parts. This is going to be number 1, just to be able to give a little bit of break between the depth and breadth of the concepts. So with that being said, what I would highly recommend as you review this video and as you study for this particular chapter, rather than sitting down and trying to do the entire chapter in one sitting, break it up like I am in the videos, or break it up into smaller sections, however it works for you. But this is a lot of information. It's covering essentially a foundational chemistry course in one chapter, or for us, 1 week. So it is a lot of information, and I would highly recommend you take the time and break it down and do it kind of piece by piece, category by category, maybe 2 sections at a time. Some are going to be easier than others. And really give yourself the time to dive into this information because it is going to be pretty heavy. So that being said, these PowerPoints are only going to be for chapters 2.1 to 2.5. So this video is going to be covering the basic chemistry sections. So before we get into that basic chemistry, we're just going to kind of do an overview of what chemistry actually is. Well, really what we care about in this world is when we're talking about chemical reactions, we need the chemistry, because we're going to be talking about chemical reactions today. And chemical reactions are going to be what underlie every physiological process. So they are responsible for everything that we do. They are very important. Some things are going to be easy, some things are going to be hard, some things are going to be only happening random, some things are going to be happening quite frequently. But these chemical reactions are what allow for all of our physiological processes to occur. So to start with chemistry, we're going to start at the very, very beginning, and that is going to be the foundation of matter. So we're going to start right here with the basic principles of chemistry. So I'm going to zoom in a little bit so we can see it. So when we're talking about matter, from a chemistry standpoint, you probably learned this definition when you were in elementary school. So it's anything that occupies space and takes up mass. So anything that occupies space and has mass. So when we're talking about it in our concepts, essentially it is going to be anything that is felt, anything that is smelled, anything that is seen, all of the things that you are able to touch or tangible items are going to kind of fall into this matter category. Just as a reminder, mass does not equal weight. Weight is going to be under the effects of gravity, whereas mass is not under the effects of gravity. So anything that we're going to talk about with matter is going to fall into 3 categories, or the 3 states of matter. Again, these are probably going to be a flashback to earlier biology classes. So there are going to be 3 states to matter. And those states are going to be solid, liquid, and a gas. So coming over here, you can see that a solid is going to be anything that has a definite shape and a volume. A liquid is going to have something that has a changeable shape, so it has the ability to morph. And gas is going to be anything that has a changeable shape and volume. So the big focus here is that a solid is going to have a very specifically defined shape, but also a very specifically defined volume. Liquid is going to have a very specifically defined volume, but the shape can change. Whereas a gas, both the shape and the volume can change. So that's kind of the foundational definition of those 3 states of matter. So now what we're going to look at next is what happens when you do things with this matter. So from our anatomical position, we don't necessarily so much care about the matter as much as it is what happens. So what we're going to look at is a concept called energy. And energy is going to be the capacity to do work, or it's going to put matter into motion. It is the ability to do work. Capacity to do work is another way to say it, or to put matter into motion. It's how you are actually moving and using the matter. There's going to be two types of energy that we're going to talk about in this class. And these are going to be right here. The two types of energy that we're going to talk about, the first one is going to be kinetic. Kinetic energy is going to be energy that is actually in action. So I'm just going to do a big E for energy. It's just way easier for notes. So this is going to be energy that is in action, meaning kinetic energy is actually doing work. It is going to be pushing. It is going to be pulling. It is actually doing work. Whereas the other one is going to be potential. And potential energy is going to be stored energy. This is not currently working. It is not doing work, but it has the potential where it could be. A kinetic energy, a good way to think about this, is a light bulb. The light bulb is actually giving off energy. It is doing work. Whereas potential energy is a battery. It is stored energy. The battery is not have the ability to do anything, but it does have the ability that when it's used, it is going to use the energy that is stored within. That's actually why when we get to the nervous system and we get to chapter 3, we're going to describe some parts of the body as batteries because they're going to act like a battery where they're going to have stored potential energy. So that's really important. These terms are going to come up a lot, so please make sure you at least know what kinetic and potential energy is. Okay, so there's a couple different forms of energy, and we're just going to talk through these real quick. I'm not going to write them down because these are great little descriptions and they're going to be short and sweet. So there are going to be there's forms of energy. The presentation that the energy can actually show up in. So the first one is going to be chemical energy. Ooh, sorry, wrong one. And when we have chemical energy, this is going to be stored energy in a chemical substance. So this type of energy is going to be stored in bonds. So if I were to put that down here, chemical energy is going to be stored in bonds. So that way, if I have an H2O molecule, so this is water, when we're talking about a bond, we say this connection point between this item and this item, which we're going to talk about a lot. This guy right here is called a bond. Chemical energy is saying that there is energy, this is acting as a battery, that is stored in this particular bond. If we were to break this bond, you release that energy, which is great. We want that. That's how our body will actually work. Another type of energy you have is going to be electrical energy. And electrical energy is going to be the movement of ions. So with electrical energy, you are actually going to have charged particles moving from one place to another. So when we're talking about this, we'll start using positive charged molecules, and then we'll talk about negative charged molecules. And these guys will actually move in a specific direction in a specific path. So electrical energy is the movement of charged particles. Mechanical energy is going to be directly moving and moving matter. So when we're talking about mechanical energy, we're actually going to be talking about moving our muscles most of the time. So this is going to be your specifically moving matter. Mechanical energy is the definition of you have energy at the end of the day, you have energy after you go on a walk. It is the ability to directly move matter. And then the third type is going to be radiant or electromagnetic, and this is going to be the energy that travels in waves. So when you've got this type of, I'm just going to do radiant, but when you have this type of energy, this one is going to travel in these types of sinusoidal waves. Light travels in this type of wave, heat, X-rays, UV light, all of those will travel in this type of wave. So those are the types of energies that we're going to talk about in this class. You will hear this chapter is going to focus on chemical and electrical energy. So one reason we care about energy is because this process right here. Energy can be converted from one form to another. So we have the ability to have chemical energy become mechanical energy, or radiant energy become electrical energy. These guys can become other types, which is very, very cool. You don't ever lose energy. Only a little tiny bit. What you do is you just convert it into a different type of energy. Okay, so that's kind of a foundational idea of what we're going to talk about. The next is we're going to do just a little bit of an overview on some other science pieces. So we're going to talk about 2.2. We're going to talk about atoms and elements. So because I'm getting a little low, these guys all go together. I'm just going to zoom out so we can move to the side. So when we're talking about 2.2, atoms and elements. So what's happening in this section? Ooh, so sorry. So when we're talking about atoms and elements, what we are saying here is first let's define what an element is. So an element is actually going to be a unique substance. And this unique substance cannot be broken down further. So it is going to be at its smallest part. It cannot be broken down by ordinary chemical methods. So I'm going to do a caveat with this. An element is something that is a unique substance that cannot be broken down by ordinary chemical methods. When I was going through early chemistry classes, this was a recent topic of conversation in the sense when I learned it, an element was really just a unique substance that can't be broken down. What we now know is that science can break down elements into its smaller form, into smaller pieces, but this will only occur under some sort of super pressurized man-made reaction. So if you've ever heard of the boson-Higgs particle, that was created and figured out because they can break down these elements by non-natural methods. So apart from all of that, when we're talking about an element, it's going to be a unique substance that can't be broken down by ordinary chemical methods. All matter, so everything else we just talked about, is composed of elements. So that means that any type of matter, solid, liquid, or gas, is going to have a unique substance that can't be broken down. There are 4 main elements that make up the human body, and these are going to be listed right here. Of these 4 main elements, when we talk about them in this class, you need to know them by their full name, but you also need to know them by what is called their atomic symbol. So I'm going to combine these two PowerPoints right here. So the 4 main elements that are going to make up the human body are going to be carbon, which will also be a capital C, oxygen, which will be a capital O, hydrogen, which is a capital H, and nitrogen, which is a capital N. These are the 4 main elements. There's also a couple other elements that we'll talk about, but these are the 4 ones that make up the human body, and the periodic table is where you will find these things. So, like I said, these right here are going to be called the atomic symbol. So whenever you look at an element and you see the shorthand atomic symbol, that's what you're talking about. As a heads up, I'm going to zoom in so we can see the charts that are straight from your book. So these are table 2.1. So up here, we're talking about all elements are made out of atoms, which we've already discussed, and then everything is going to have an atomic symbol. So talking about the 4 most common elements in the human body, those were these guys: carbon, oxygen, hydrogen, and nitrogen. And you can see there is their atomic symbol. Well, these are some other common elements that we're going to talk about in this class. And here are their atomic symbols. So we're going to talk about calcium, Ca, phosphorus, capital P, potassium, K. You'll notice that the phosphorus and the potassium do not both start with P because these atomic symbols are unique. So phosphorus is the P, but potassium is going to be a K. Sulfur is an S, sodium is Na, chlorine is Cl, magnesium is Mg, iodine is I, and iron is Fe. You'll notice with iron it is not I or it's not Ir, it's actually Fe, which stands for ferrous, which is the Latin word for iron. So those are the ones that you do need to know and be aware of. Okay, so that's the atomic element. That's the atoms, or sorry, that's the start of this next section, which is going to be on actual structure and talking about atoms. So when we are talking about atoms, what we are saying with these guys is these are the building blocks of elements. These are the building blocks of elements. So if you take these very small pieces and you break down that element by non-chemical methods, non-normal chemical methods, you can get these building blocks of elements. And they're going to be these things called atoms. And they are going to be made up of subatomic particles. These subatomic particles are also terms you've probably heard. Protons, neutrons, and electrons. So we are doing a lot of chemistry for this first section. So protons, when we're talking about these subatomic particles, what I like to do is we're going to make a little chart. So I'm just going to zoom on over and we're going to make a chart of our protons, neutrons, and electrons. But first I'm going to erase them so now that we know what we're talking about. And here's my chart. When we are talking about these atoms, we are going to talk about this symbol, what you will see when we're talking about it. We're going to talk about the electrical charge. Will it have a positive or a negative? We're going to talk about the mass. What is the mass of the subatomic particle? And then we're going to talk about where you can actually find it in the element. So we're going to talk about these 4 things, and we're going to talk about it for a proton, a neutron. Let me just give a little bit more room. Proton, neutron, electron. So we're going to break these guys down. Okay, so essentially we're just focusing on this. We're just going to make it a little bit easier. I like doing charts because I think it really helps understanding how things relate to each other. So looking at this, with our atoms, our protons, neutrons, and electrons, the charge for a proton is a positive charge. And the symbol for a proton is a little p with a positive charge. So that's the symbol for a proton. The symbol for, or the charge for an electron is a negative charge. So we've got a positive charge and we've got a negative charge. The symbol for our electron is a little e with a negative. So that kind of makes sense. A neutron is going to be no charge. It is neutral. And its symbol is an N with a neutral charge. So this way, when you see a proton, you need to know that it is a positive charge, an electron is a negative charge, and a neutron is just essentially right in the middle. It does not have one. So the mass of these guys is actually very important. Your electron is a negative charge, but it is actually going to be a 0 mass, or what is called an AMU. And this stands for atomic mass unit. So an electron carries 0 measurable weight. This is essentially almost like a cloud. It is something that you are not actually able to measure the mass. Whereas the proton and the neutrons, you can. These are both going to be 1 AMU. So they have the mass of 1. So they weigh the same. Or not the same. They have the same mass. And then where you actually find these things is what we're going to talk about next, is the location and what the atoms look like. So the location of the proton and the neutron is the same. These will be found in the nucleus of the atom. Whereas the electron is going to be found in something called the electron orbital cloud. electron orbital cloud. So if you look at this chart, this is really all you need to know to be able to start with the foundational understanding of all of these atoms. What I'm going to talk about next is how this charge, mass, and location kind of comes into play. So we're going to zoom in on these PowerPoints real quick so we can talk through those. Okay, so the structure of an atom right here. When you're looking at an atom, the number of positive protons is going to be balanced by the number of negative electrons. So atoms are going to be neutral. And the protons and the neutrons are going to be found in a centrally located nucleus. So I wanted to highlight that because I'm going to drive on over here and we're going to draw that out. So our proton and our neutrons are going to be found in the nucleus. So I'm going to do a couple different colors for these guys. For my proton, here's my nucleus, and inside my nucleus I will have a proton. Proton, proton. But what this description just said is that the number of positive protons will be balanced by the number of negative electrons, or negative electrons. So atoms are going to be electrically neutral. And then we're going to talk about protons and neutrons are found in the nucleus. So if I have 2 protons here, I'm going to have 2 negative ions here because there has to be 2 protons and 2 neutrons in my nucleus because they have to match. And then what we're going to do in our electron cloud right around the outside is where we will find our, is our electron cloud? This is where we will find our 2 negative ions. So our 2 negative elements. So if you're looking at this, we are going to have our nucleus, our neutron and proton are going to be found in the nucleus. Our electrons are found in this electron orbital cloud. Our positive and negatives are going to equal out because it needs to be overall, needs to be neutral. So I'm going to have 2 electrons that are negative like that. And then I'm going to have 2 positive protons that look like that. If I have 2 negatives and 2 positives, you are going to have a neutral overall. So that's what that statement was saying. Okay, just to give a little bit of an understanding, you'll see these 2 descriptions called a planetary or an orbital model. This is not super important, but it's just to give you a little bit of background on drawings. So a planetary model is essentially going to be what I drew, where you've got a center nucleus, and then your electrons will be in an orbit around it. So this is the planetary model. You've got the nucleus, and then you've got the electrons floating around it. That's what I drew. But there's also a model out there called the orbital model. And the orbital model is essentially that these are going to look like clouds or orbitals, where it can be found anywhere in this orbital. Whereas the planetary, it has to stay on this actual axis all the way around. So that's the difference between the two, is the orbital kind of says that they can float anywhere within that space, where the planetary, they need to stay on that line. That is just a description to let you know that when you see these 2 things, they are the exact same. It is just 2 different ways to show the same image, but that's all that means. Okay, so when we're looking at these elements, different elements are going to contain different numbers of subatomic particles. So this is how we're going to get our different elements, is we're going to be able to have different levels of protons, different levels of neutrons inside our element. So up here, we're going to talk about through these guys real quick. So to give you an example, when you have hydrogen, remember hydrogen is an H. It has 1 proton, 0 neutrons, and 1 electron. That is what makes hydrogen hydrogen. Helium, which is He, has 2 protons, which is positive, 2 neutrons, and 2 electrons. So guess what? If you look at that right there, and you know that helium has 2 protons, 2 neutrons, and 2 electrons, this is what I drew right here. So that way you can see that there are 2 of everything. So I actually drew that element, which is helium. So the different elements are going to have different types of subatomic particles, with different numbers of subatomic particles. So we talked about hydrogen and helium, and then there's also an example of lithium. So what I drew is helium, but you can see right here, hydrogen and helium, 1 proton, 0 neutrons, 1 electron. Same thing for helium. Okay, so when you're looking at these elements, what you'll be able to do is you'll be able to tell how many protons are going to be found in the nucleus. So this is going to be called the atomic number. And the atomic number is important because it will actually tell us the number of protons. And as it's telling us the number of protons, remember the number of protons is always going to be equal to the number of electrons. So the atomic number specifically tells us the number of protons, but because the number of protons has to equal the number of electrons, and the reason for that is this is a positive and this is a negative, so they have to be the same in order to be neutral. The atomic number is basically able to tell us the number of protons and the number of electrons. So whenever you see this, you'll just see it as written this way. We're not going to spend a lot of time on how to write chemistry because we're only talking about the specifics that relate to this course, and we don't really talk about writing chemistry a whole lot. So I'm going to skip on over mass number, isotopes, and atomic weight. But here you guys can see those examples again. Again, I am not going to spend time on radioisotopes or isotopes. So you guys can knock that off your list. Okay, so moving on to 2.3. This video is going to go through 2.5. So 2.3, what is happening here is we are starting to combine matter. What happens when we put different elements together and different types of substances together? So with what we're doing here is we're combining things. So atoms are really cool, but atoms are not found in a free state, meaning they are not found just hanging out by themselves. They are always found in connection to other atoms. They are always bound to other atoms. And when they are bound to other atoms, that has a name, and that is going to be called a molecule. So that's this guy right here. A molecule is a general name for 2+ atoms. Is a good way to remember it. 2+ atoms. If you have 2 atoms or more, you're going to create something called a molecule. Okay, as we're going, these molecules, one fun fact is these can be the same atoms, or these can be different atoms. They just have to be 2. So it could be hydrogen plus hydrogen, or it could be hydrogen plus oxygen. Those are 2 atoms, but they're also the same and they are different, but that is a molecule. You can also have something that is called a compound. And a compound is going to be 2 or more atoms, so it's going to be very similar, but these are going to have to be different kinds of atoms. So these must be a hydrogen plus an oxygen, or a carbon plus an oxygen. A compound has to be 2 or more different atoms. So an example of this that you're going to see is sucrose, which is over here, C6H12O6. We are combining 6 carbons, 12 hydrogens, and 6 oxygens. Because those are different, those are going to be called a compound. Okay, when we put a bunch of compounds together, when we put 2 or more atoms in together, you're going to get something that is going to be called a mixture. So a mixture is another term. So we've got molecule, we've got compound, we've got mixture. A mixture is going to be some sort of substance that is going to be made up of two or more components. So we are adding even further. Whereas a compound was two things that were different, a mixture is going to be two or more things that are going to be made up of things that are different. So a mixture is substances that are made up of two or more compounds. And there are three basic types of mixtures, and we're going to talk through these real quick. So there are three types to a mixture. The first type is going to be called a solution. This is the one we most commonly use in our everyday environment. So a solution is this guy right here. And with a solution, what this is actually meaning is that this is a homogeneous mixture. It is a homogeneous mixture. And what that means is that is the same mixture all throughout. So if you were to take a glass of water and you were to dump a bunch of salt in and get some sodium chloride in there, what you'll eventually get when all of that dissolves and melted is you will get salt water. If you are to take a bunch of salt water from up here and you take salt water from down here, they are going to be the same. The mixture inside doesn't, once you put everything together, the mixture everywhere will be the same. It does not matter where you pull it from. Okay, when we're talking about this, you'll notice that I did a liquid and a solid. That is typically what happens. So this is a big component right here of solutions, the solvent and the solute. These are a very big premise that we're going to spend a second on. So when we're talking about that, we're going to take my salt water example that I just drew. And this, my salt water, I had a liquid and I had a solid. I had the thing that did the dissolving, and this is the thing that was dissolved, right? So with this, we're going to focus on the thing that's the dissolving and the thing that's the dissolved. So with a solution, you're going to have a solute and a solvent. A solvent is going to be the thing that is going to be in the greater amount. It is usually liquid. It is usually liquid. That's this. Not only is it usually liquid, in the body, it is usually going to be H2O. It's normally going to be water. So the so sorry. Nope. Guys, erase everything I just said. Erase. The solvent. So we're going to back up real quick. The solvent is normally in a greater amount. Everything I just said is true, but it's going to be for solvent. It is in the body. It's going to be the thing that is going to be usually a liquid. It's going to be dissolving. And in the body, it is going to be usually H2O in the human body. In a traditional chemistry lab, it can be a variety of other things. But in the human body, the solvent is normally water. The solute is the substance that is dissolved. That's going to be the salt in this example. It's usually going to be a solid, but not always. It could be a gas. It could be another liquid. But it's the substance that's going to be dissolved. So the solvent and the solute are going to be really, really important. An example and a good way to remember this is how I was taught, and it's very cheesy and elementary, but it works. So solvent has the V. And if you think about the V as being a little bit of a jaw, that's going to eat. It's going to eat the solute. So the V of the solvent is going to be responsible for dissolving and eating up and destroying and being the bigger substance to the solute. So I don't know if that's helpful, but that is one way I was taught it, and I do think that that kind of helps it stick in your head a little bit. Okay, so that's the solute and the solvent. When we're talking about a solution, those are some terms that you are going to need to know. Okay, so moving on to the next type of a mixture. We are going to skip this section right now, and we will come back to it a little bit later. So what we're going to do is we did our solutions. Now we're going to do our second type, which is our colloids. So we're going to do type number 2, and then suspension is going to be type number 3. So solutions was type number 1. And again, we are going to come back to this later. So with this colloid, let me see if I can zoom in. So this type of mixture is going to be something that is also called an emulsion. So this is going to be a heterogeneous mixture. So this mixture is heterogeneous, which means that it is going to be areas that are different. So if you were to do what I described earlier, and you were to put two substances together, and you have a final result, if you take something from this section and something from this section, they are actually going to have a different state of matter. This one up here could be super, super chunky. And this one down here could be super fine or not at all there. But if you were to take pieces of that actual mixture, they're going to be different, which makes it a heterogeneous mixture. A good example of this, if you think about it, is going to be Jell-O, because this type of mixture is normally something that will change states and go from liquid to solid. So with Jell-O, if you were to get the right amount of water to go with the right amount of the powder, at some point as it's making that state from liquid to the Jell-O consistency, there would be partially things that were dissolved, other parts that weren't dissolved. A colloid is a great example. A Jell-O is a great example of a colloid. Okay, so the third type of mixture that we're going to talk about is going to be a suspension. And the suspension is another easy one to understand. Colloids are the ones that are a little bit more complicated. So suspensions are also going to be a heterogeneous mixture. But this is going to be slightly different. So this is going to be a heterogeneous mixture, and it will have solutes that settle out. Meaning, whatever solute you have put into your solvent, so in my example here, I'm going to do sand, and I'm going to dump that into my H2O. At the end of the day, what you're actually going to get is, do you have the sand fully dissolved? No. You are going to end up with the sand at the bottom. So you will not actually dissolve the substance. The solute will be able to be strained back out. That is an example of a suspension. Another example is blood. The blood cells are not going to become part. They don't dissolve. They will actually be able to be pulled out. Okay, so when you're looking at these, we're going to talk about why we care about mixtures and compounds, but we're going to care about them in the premise of chemical bonds. So, unlike compounds, mixtures do not have chemical bonds. So that means this next section we're going to talk about are not mixtures. This next section is going to be compounds. And compounds can only be separated by breaking their chemical bond, which means that we can only break and get that energy out if it was breaking of two bonds, or bonds. Okay, So to then move on to this next section of 2.4, we're going to come down here. So I am going to move this over here. Cool. Okay, so now we're looking at 2.4, chemical bonds. So when we're talking about chemical bonds, remember we are talking about, these are going to be atom to atom connections, and these are energy relationships. So with a chemical bond, it is an atom to an atom connection. And having these bonds is a storage of potential energy, so it is going to be an energy relationship. Some atom to atom connections are going to have more energy, some are going to have less. But when you break the bond, what you will actually do is you will be able to release the energy, or you will be able to gain energy by breaking the bond. So we're going to talk through a couple ways that we do this. This is a decently complicated process, so we're just going to focus on some of the highlights for chemical bonds. So when we're talking about chemical bonds, remember we're breaking these connections. So first of all, let's talk about how these connections are organized. So we're going to start up here at something called electron shells. And then we're going to do this thing called valence shells. And then we're going to go and do an octet rule. So when we're talking about these chemical bonds, and it's the atom to atom connection, we're talking about how they are actually connected to each other. And the way they are connected to each other is through electrical electron shells. So briefly, so the way we do this is because we are going to talk about how they are actually organized. That is the way that you will do this. So with these chemical bonds and these electrons, what we're actually talking about is something that is going to be called an electron shell. And an electron shell is going to be electrons forming a shell around the nucleus, the atomic nucleus. So as they're doing this, if we have our nucleus right here, I'm just going to do a big capital N for nucleus. And we have our electrons in a shell all the way around it. That's what we mean. But what we need to know is that this electron shell will have different energy levels. There's multiple shells, and they will all have different energy levels. So not only do they have different energy levels, they're going to be either close to the nucleus, or they're going to be far, far away from the nucleus. And the distance away from the nucleus that they are is going to be giving them their energy. So the distance will determine energy. So let's talk through that real quick. That is what these guys are called. So when you're looking at this electron shell, here's my nucleus. I'm just going to blow it up down here. My atomic nucleus. You will actually have something called shells, and these shells will be 7 of them. So of these 7 shells, my drawing is not fantabulous. You'll go all the way up to 7 different layers of shells. So we've got 1, 2, 3, 4, 5, 6, 7. So there are going to be 7 layers of shells, specifically electron shells. And the further you go away from the nucleus, you will have an energy level. So here we go. if I am going to have an electron way out here, an electron that is way out here, the furthest away from that nucleus, the farther away from the nucleus will have the greater potential energy. Because remember, we're breaking these bonds. So right now it's potential energy. So an electron that lives way out here in the 7th electron shell will have greater potential energy if we break the connection between these bonds. Whereas if there is a cell or an electron that is this close to the atomic nuclei, the closer it is, the less energy. It will have the least amount of potential energy. So what we're going to be looking for is when we start going through some of these things is you are going to start wanting these guys. You want the guys way out because that means if you break the bond, you're going to have the most potential energy. So this is an example of the electron shell. What I want to tell you about this thing called the octet rule. So I'm just going to drive over real quick. The octet rule, octet means 8. So there are 7 layers of shells, which is awesome. That's super easy to remember. But this octet rule, essentially means 8. And what it means for this is that within all of these cells or shells, all the way up from these shelves, within these 1, that's the closest, 7, that's the furthest away, you can have only 8 electrons per shell. So there can only be 8. That's the octet rule. There can only be 8 electrons per shell. If there is any more, you cannot have more than 8 electrons. You are not able to have more than 8. But you can have less than 8. If you have less than 8, let's say you have 6, that means you are going to have the availability for how many electrons in order to get to 8? You have the availability for 2. Because not only does it only have 8 electrons, it really wants 8 electrons. So in order to do that, it will either lose electrons to get to 8 or it will gain electrons to get to 8. So that is the octet rule. And the way it will gain or lose is in order to do that will be by breaking these chemical bonds. So to go over and show a couple examples of these guys. When we're talking about the outermost shell, or the outermost is going to be the highest potential energy. Remember that. So these guys like this, up here at our octet rule, right here, atoms will gain, lose, or they can share in order to have the stability of 8 electrons per shell, because they want to have 8 electrons in their outside shell. So here's an example real quick we're going to go through and talk through. Helium, neon, and then the 4 chemically reactive. So if you look right here with these guys, we have in our first shell, also just to tell you that, in your first shell, you can only have 2. So in shell 1, you can only have 2 electrons. It is every shell after that that wants 8. So here we've got our 2 electrons. He doesn't want to gain or lose. He's good. Our first shell has 2 electrons. Our next shell wants 8, and it has 1, 2, 3, 4, 6, 7, 8. So he's good. He does not want to share or lose any electrons. But let's come over here and look at hydrogen. All the way out here, we only have 1. So that means we have availability for 1 electron, because 1 plus 1 equals 2. We look over here with our carbon. We have 2 in our inside. That's good. Our outside layer only has 4. 1, 2, 3, 4. If we have 4 electrons and we want 8, we have the space for 4 more. Because remember, we want 8. Over here, we've got 2 on our inside, so that's good. But then on our outside, we have 1, 2, 3, 4, 5, 6 electrons. So if we want 8, that means we have availability. We want to get 2 more electrons. And then over here in sodium, 2 on our inside. Look, we've got 8 on the middle. That's awesome. And then this outside layer, we only have 1 electron, which means we want 7 electrons. I'm going to go ahead and tell you, getting 7 electrons in order to equal 8 is going to be really, really hard. So what we'll actually do is we will want to lose 1 electron. And if we lose this guy, the outside layer will be 8 and you'll be good to go. So the way these chemical reactions are going to work, you do not need to know how to draw these chemical reactions. You do not need to know how to fill in and do orbitals. We're not going to do SPs. We're not going to do sp2s. You just need to know that the layers, the reaction of these compounds is going to be based on gaining or losing electrons because it wants to have the right amount of numbers. And you need to be able to understand what's happening with these, but drawing them, you do not need to be able to create these from scratch, but you need to kind of understand what's going on. So the way we are going to either gain or lose these electrons is going to be by breaking these chemical bonds. So to start with, we're going to talk about the types of chemical bonds that our body has before we can actually break them. So the types of chemical bonds that we will have throughout chemistry and also in our body. So these will be types of chemical bonds. There are 3 types. The first one is going to be ionic. These ionic bonds. So when we're talking about ionic bonds, this is going to be a chemical bond where you are going to transfer an electron. One or more electrons. So a chemical bond, you are not sharing, you're literally giving it away. You will gain one or you will lose one. Whenever you have an ionic bond, you're going to transfer one or more electron. And as you're transferring it from one shell to the other. So if you were to do any kind of Christmas giving a gift, a birthday gift, any kind of gift where you are transferring something or giving something, you're always going to have something that will lose whatever item, and then you'll always have something that will gain whatever that item is. And ionic bonds are the same way. So whatever atom is going to lose the electron is going to be called a cation. A cation is going to be the molecule or the atom that loses the electron, whereas the one that will gain the electron is going to be called an anion. So if you think about it, remember we are going to gain or lose an electron. To think all the way back to the first part of this course when we started talking about this, is these are going to be negative. So what we are doing is we are transferring a negative ion. So if you are losing an electron, you're losing a negative ion. What is actually happening is you are losing that negative ion, so you will become more positive. It's a double negative. When you lose in an ionic bond, you're losing the negative ion, you're losing the electron, which means if you get rid of it, you're becoming more positive. Whereas with an anion, when you are gaining that electron, if you gain the electron, you are gaining the negative, you are going to become more negative. You can also hear these terms as an anion is going to be an electron acceptor because it is going to gain it, it's going to accept it, whereas a cation is going to be the electron donor because it gives it away. So these are also terms you're going to hear. But that's what's happening with an ionic bond. You are giving away. You are not sharing. You are essentially gifting. But when you do that, something has to lose it and something has to gain it. Too far. Back to our example on the slide. So we're looking at this ionic bond right here. This sodium and this chloride item, this is what we're going to look at. So here we are going to have, let's count them, 1 in our outside layer. And here we have 1, 2, 3, 4, 5, 6, 7. Remember, we want 8. So this guy right here is going to be given to this guy. If he's given, that means we no longer have the outside. And this guy will now have 1, 2, 3, 4, 5, 6, 7, 8. So he's going to be happy. He has his 8 electrons. And then this guy's going to have 1, 2, 3, 4, 5, 6, 7, 8 electrons as well. So he's going to be super happy. This is sodium chloride. This is a very stable compound because these like to give or gain an electron. With this component, your sodium right here was the thing that gave the electron. So if it gives the electron, the sodium is the cation or the electron donor, whereas the chloride is going to be the anion, otherwise known as the electron acceptor. So that's how those two terms will come into play in a real life example. So you can see how we are giving away the electron. There is no connection between the two. They are just staying next to each other because they like each other, but there is no actual connection. So that's a great point. So why do these ionic bonds stay together? So the reason ionic bonds are going to stay together is because opposites attract. So when you actually put that positive and that negative next to each other, they will stay together because opposites will attract. So you will have the positive attracted to the negative. And so they will essentially just hover next to each other. They are tethered by that attraction of positive and negative. So that's an ionic bond. The second type of chemical bond we're going to talk about is going to be covalent bonds. And this is going to be the most common type that we're going to talk about. Covalent bonds are actually going to be the sharing of electrons. So it is a chemical bond that is formed by sharing electrons. And remember, this sharing of an electron is going to be negative. So as we are sharing 2 or more atoms, these covalent bonds are going to share these guys. And what it happens is it allows for each of these atoms to have that outside layer fully connected, which is great because that is what they want. So the way they're going to share these is when they actually create this bond, they will share the electron in the outermost electron shell. So the way you're going to shell it, these are going to be super, super stable. If you share an electron, each atom is going to be stable. And what also happens is you can have sharing of lots of electrons. You can share a single pair, and you can be called a single covalent bond. And if you are a single covalent bond, it is going to be a type of sharing where it is two atoms, and they are going to share one pair of electrons. So that means a single covalent bond will be sharing a pair of electrons. It looks like that. There are two. That's a pair. You can also have a double covalent bond. And this is going to be two atoms that are sharing two pairs of electrons. So that will be, here's my one, here's my second. Two pairs of electrons. Or you can have a triple covalent bond. And with a triple covalent bond, you have two atoms, three pairs of electrons. So this guy is going to be 1, 2, 1, 2, 1, 2. Three pairs of electrons. So this is how you have some covalent bonds. So we're going to zoom up here, and we're going to look through some of these examples for these covalent bonds. So starting at this guy right here, figure 2.7, I believe. So we're going to be looking at a hydrogen atom and a carbon atom. So when we're looking at this right here, with our hydrogen atom and our carbon atom, remember we are doing covalent bonds, so we are sharing our ions. I'm trying to zoom in so we can see it. There we go. So as we zoom in, you'll notice, let me do a little bit more. So this guy right here is going to be 4 hydrogen ions. So it's going to be a hydrogen ion times 1, 2, 3, 4. There are 4 of them. This carbon atom has 1, 2, 3, 4. So it has an open space here, an open space, open space, and open space. So there are 4 open electron spaces. This has one that it can give or share. This has one that it can share, he can share, and he can share. So what happens is your carbon will still have its 1, 2, 3, 4, and your hydrogen will still have its 1, but they are sharing those 2 between them. So between them they have 1, 2, 3, 4, 5, 6, 7, 8, which means it is a very happy compound. So that's going to be that single covalent bond that we talked about. The double and the triple covalent bond are going to be the same thing, where they are sharing pairs of electrons. So when we're looking at the double covalent bond, this guy right here has 1, 2, 3, 4, 5, 6, 6. That means there are 2 open. This guy right here is 1, 2, 3, 4, 5, 6. That means there are 2 open. What will happen is we'll have 1, 2, 3, 4, 5. There was that 6. He'll come and then he will share with his. And you will get that double bond. So it'll be 1, 2, 3, 4, 5, 6 of one. 1, 2, 3, 4, 5, 6 of another. So they are sharing 2 pairs of electrons. This one came from this compound. This one came from that one. And then the same thing is true for our triple bonds. These guys are going to come together, and these 3 are going to be shared between them. So this molecule of nitrogen has 1, 2, 3, 4, 5, 6, 7, 8. This molecule of nitrogen has 1, 2, 3, 4, 5, 6, 7, 8. So they both have 8 electrons. They are super happy because they are sharing 3 pairs. So that is what's happening with the covalent bonds. The third, oh, hi. We're almost done with this section. The third type of chemical bond we're going to talk about is going to be called a hydrogen bond. And a hydrogen bond is only going to be between hydrogen molecules. Okay, let me get up there. So the third type of hydrogen bond is going to be a hydrogen bond. And a hydrogen bond, like I had mentioned, is only going to be an attractive force between hydrogen molecules. So that's why it's actually going to be in the name. It doesn't work with carbon, it doesn't work with oxygen. It's only going to be an attractive force between hydrogen molecules. And what's going to happen with this is it is going to be a weak magnetic attraction where these two hydrogen bonds are going to come together. So if we have H2O, which is water, and you're going to have another H2O, which is water, we're talking about the connection between these two hydrogens. So then if you have an H2O down here, you're going to have these guys connected. And you will actually create the water. This hydrogen bond, this attractive force between these two molecules, is what allows for this surface tension when you see specific bugs or plants or that kind of thing floating on the surface and not sinking. It's because they don't carry enough weight to be able to break these bonds. So it's actually going to hold them up. That's how you get that surface tension. So it's cool. Okay, the last section for today is going to be 2.5. We've done all of our elements, we've done our atoms, we've done the different types of compounds and mixtures when we put atoms and elements together, and then we've talked about what happens when we connect them and create bonds, and now we're going to talk about what happens if we need to break those bonds. So this is going to be chemical reactions. Chemical reactions. When we are doing chemical reactions, we are going to be breaking a chemical bond. And the reason we are breaking the chemical bond is it is either going to be broken, rearranged, or you're doing it because you're going to form new ones. So when we're looking at these chemical bonds, we're breaking them to rearrange them, to break them completely, or to form new bonds. So with these chemical reactions, it is going to be essentially written like an equation. So it's going to have A plus B equals C. This is what you will see as a chemical reaction. These sides are going to be reactants. They are the ingredients. These are what is happening. These are the things that are getting broken, rearranged, creating new. And then this side will be the products. And this will be the new formed whatever the outcome is. So I like to think of the reactants as the ingredients and the product is the actual cake. It's the outcome. It's the results. So chemical reactions are going to be built and written like a chemical equation. There are 4 types of chemical reactions that we will talk about in this class. So there are 4 types of chemical, 4 types of chemical reactions. We're going to start with the simple one, and I'm going to do RXTN because that stands for reactions. I'm going to do the simple one, and then we're going to get more complex. So the first one is going to be called synthesis, otherwise known as a combination reaction. Synthesis means to create something. You are going from nothing and you are creating something. So with a synthesis reaction, you are going from a small atom, You are combining into larger atoms. So that's why it's got the name combination. So with a synthesis, you are combining atoms into larger. And as you're doing this, you are building essentially up. So an example of this is A plus B. If I put those together, I will get AB. AB means that there is a chemical bond between these somehow. So an example of a chemical reaction is going to be a real life chemical reaction, not the AB example, is going to be, let's do carbon plus 4 hydrogens, and you are going to get CH4. So we've combined these together. You can see how we've got small, and then you're going to big. The second type of chemical reaction is going to be a decomposition reaction. A decomposition reaction. And if you think about a decomposition, it's going to be the opposite of synthesis. So this is where you are actually going to be breaking down the molecules into smaller. So with a decomposition reaction, I am not building, I am breaking down into smaller. And this has decided to not play to right for the last remaining part of this chapter. So I apologize for this. So for this, what we're going to do is we're just going to follow along with this right here. A decomposition reaction. You are breaking down into smaller parts. So the example that you see right there is you're taking that long glycogen chain and then you are breaking it down to smaller individual parts. So an example of this would be AB is going to become A plus B. Because remember, this is the reactants, this is the products. So the result is smaller. The next two chemical reactions are the most complex ones, but they're also going to be more of the important ones because they deal with the majority of our physiological reactions in our system. So as a note, when it comes to these chemical reactions, I don't expect you guys to be able to draw them, write them, balance them. This is not a chemistry class. I just want you to be able to recognize what is happening and have an idea and the understanding of what is occurring in each type of reaction. But again, I'm not going to give you a list of a bunch of molecules and ask you to balance an equation. That is a chemistry class. That is not us. I don't like doing it either, so I'm not going to make you guys do it. So an exchange reaction is the third type. So with an exchange reaction, you are doing synthesis and decomposition. So you are doing synthesis and decomposition. So basically you are exchanging things. You are breaking down and then you're building up. So if I had AB as one molecule and I'm adding a C molecule, if I were to do an exchange reaction, I'm going to switch these guys out. So I'm going to get AC plus B. That is my outcome. So essentially you're going to switch the products and the partners because you're breaking everything. So what you did in the middle was this, and then you put it back together up here. So that's what's happening in exchange reaction. And then the fourth and final one that we're going to talk about is going to be called an oxidation reduction reaction. And again, this one's a little bit more chemistry than we're going to go into, but we're going to talk about the concept behind it. So an oxidation reduction reaction. Oxidation reduction reaction. But you will also see this titled as redox, a redox reaction. So a redox reaction is where you are going to also do the same thing of that exchange reaction. You're going to break down and you're going to build up. But what you're doing is you are specifically doing this in living systems. So it is the same premise of the decomp and synthesis, which we just talked about in an exchange reaction, but this is specifically inside living systems. So that's really the major difference. You just need to know that what we'll be talking about is redox reactions, not so much exchange reactions. And the reason you're going to do this is you're going to get some sort of energy, usually going to be due to food. So that's going to kind of what's going on in an oxidation redox reaction. So all of these are chemical reactions. The goal, remember, is to break the bond and you will get energy. So that means every time we go from AB to A plus B, and we have broken the AB bond, you are going to get some sort of energy that is released during this process. That is the entire premise behind biochem that we're going to talk about in the next couple sections in a different video, which will be when you release this energy, what does your body do with it in order to make it productive from a physiological symptom? So when we're breaking the bond and we get energy, you have released energy. This is an example of what is called an exergonic reaction. So that means that right here, too far, an exergonic reaction, this guy right here, we have broken a bond, we have gotten energy, we have released this energy. This is an exergonic reaction. Think of exodus, think of exit, think of export. All of those are going to mean out. So that means energy is released out. But then you also have the other type, which is going to be an endergonic reaction. And this is where you're going to create a bond. If you create a bond, you're going to use energy. So this is going to go A plus B, and you're going to get AB. When you do this, this is an endergonic reaction. So that's what's going to happen with these bonds. So that's going to be the kind of the end of this section of chapter 2. Whenever you have these types of chemical reactions, what I want you guys to be aware of is when you have these reactions, they're awesome, they're great, but you can control them. So there are ways that you can actually control the rate of interaction of the reaction. And that is what I want you guys to focus on and look at right in this last section right here is how do you control the rate, and rate will also mean speed of the reaction. So this is awesome that we have all of these things occurring, but what if I want it to go faster? What if I want it to go slower? You can actually control the rate of this reaction, and you can control it 3 ways. You can increase the temperature. If you increase the temperature, you increase the speed that the reaction occurs. So the hotter it is, the faster it happens. This is an example of boiling. If you were to, when you boil an egg, you are changing the structure of the egg, so you're creating a chemical reaction. If you boil it hotter, it happens faster. So that's what's happening there. You can also increase the concentration or how many pieces are involved. If you increase the concentration, you're going to increase the speed. If you have more people who are rowing on a rowboat, it will go faster. So more concentration is going to be more speed. Or you can have the particle size of these chemical reactions be affected. So if you have a smaller or a decreased particle size, you will increase the speed. So my example here is because this is opposite. If you decrease the particle size and make it smaller. So if you are on a highway on 285 and you are driving a tractor trailer truck, which is massive, or you are driving a little sport car like a Miata, BMW, Lexus, pick whichever one is your favorite. The smaller the car, the faster it goes. You do not go that fast if you are driving one of the big tractor trailer trucks. So that's how you decrease the particle size, and you can actually increase the speed of the reaction. So those are some ways you can actually affect and make these reactions happen quicker and or slower. So just keep in mind with these guys, if I decrease the temperature, what do I do to my speed? If I decrease the amount of the concentration, what do I do to my speed? And if I make the size much bigger, what do I do to my speed? So be able to do those the opposite way as well. We're going to talk about catalysts in another section, but feel free to read through and know what that is. But we are going to talk about catalysts a little bit later. So that's the first part of chapter 2. That is 2.1 to 2.5, basic chemistry. The next video will cover the biochem portion. So this was just chapter 2.1 to 2.5.